All right, we're going to do some quick notes that are a review from Algebra 2 last year about power and polynomial functions. You're going to need to use Desmos partway through the notes, so just keep that in mind. Okay, so a polynomial, the definition is simply that it's a monomial. Monomial just means one term, or the sum or difference of monomials, multiple terms. Okay, so all that means is an example of like a monomial would be something like 3x to the fourth. That's one term. If I add something else like x squared, now that's a polynomial because it has multiple monomials. When we write things in standard form, we just write them in order from highest to lowest power. So we write the terms in order highest to lowest power. So for example, we might have something like negative 2x to the fifth plus x to the fourth minus 5. So we've written those in descending power order. The first term has a power of 5, the second one has a power of 4, and the last one actually has a power of 0. Okay, so when we talk about polynomials, we're going to talk about the degree of a polynomial. And when we do that, we're really only talking about the power of the first term when it's in standard form. Okay, so when we're looking at, for example, the one we just wrote, that is a degree 5 polynomial because the power of that first term is 5. The leading coefficient is simply the coefficient in front of the first term in standard form. So the coefficient of the first term in standard form. So the key here is we have to be in standard form to understand what the leading coefficient and the degree are. So in this case, the leading coefficient here would be negative 2. Okay, so what you're going to do is pause the video here and go to Desmos. You're going to sketch, or you're going to kind of graph and then sketch, these power functions. And so you just kind of want to take a look at them. I would recommend when you're graphing them, just kind of make all of these like the same scale. So these would be like 1 and negative 1. That way you can kind of get an idea of what's going on, and how they're the same and how they're different. So go ahead and do that now and then come back to the video. Okay, so hopefully you went over to Desmos, you typed in these different power functions, and these first couple that we asked you to do, x squared, x to the fourth, x to the sixth, x to the eighth, x to the 10th, they all had some points in common, like 0, 0, 1, 1, negative 1, 1. But the shape of the graphs look a little bit different. But let's talk about what they have in common. When we look at these, we can say they all open up. We can also say they all have y-axis symmetry. And that means these are all even. And that makes sense because the exponents are all even. When we look at the next set of power functions, y equals x, x cubed, x to the fifth, x to the seventh, x to the ninth, these don't open a certain way because their arrows are going different ways. But we can say that these are all increasing. Right? As we look left to right on the graph, the y values are always getting bigger. We would say all these graphs don't have y-axis symmetry. What they have is origin symmetry. Right? If we rotate it 180 degrees around the origin, they'll look exactly the same. And that means these are all odd functions. Okay, so these are all power functions. And power functions have this form where it's like f of x equals some coefficient times x to the n. One of the key features is it is just a single term. All right, so there's nothing added or subtracted here. It's just one term. And the even power functions that we talked about would be y equals x squared, y equals x to the 4th, y equals x to the 6th, and then we said they all have y-axis symmetry. As you looked at those, the shape of the parabola from x squared, when we moved to x 4th, got a little more sort of squared off at the corners, and the higher the power, the more squared off it looked. Our odd power functions are going to be y equals x, y equals x cubed, y equals x to the 5th. And those all have origin symmetry. Now each of these functions, well, almost all of them, have a name, right? Y equals x is linear, sometimes called the identity function. X cubed is cubic. And x to the 5th is called quintic. Like a quintet, a group of 5. X squared, we know that one really well. That's quadratic. X to the 4th is quartic. And after the degree 5, they don't really give them special names. So x to the 6th doesn't get a special name. Okay, so we're going to take what we know now and sketch some of these graphs using transformations, right? So we're going to look at the fact that this first graph, y equals the quantity x minus 1 to the 6. We would say, you know what, that x minus 1 is shifting to the right 1. And then since I know it's a power 6 function, it's going to have this general shape, but the edges are going to be kind of squared off a little bit. So I'm going to move to the right 1. And we still go over 1, up 1 on both sides. The only difference is it's kind of going to be sharper turns at those turning points. When we look at the next one, we have a couple transformations. First of all, let's identify that it is quintic, it's degree 5. And it's actually not a power function when we shift it, but we'll still use the fact that we know about these power functions. And we'll say this one is shifted down 3. And also reflected down. So I'm going to take the fact that normally we would put a point right here. We're going to move it down here. And if this was a normal degree 5 function, we'd put points here and here. But because it's reflecting, I'm going to reflect those. So I'm going to take away those other points that we don't need. This way, instead of it being increasing, it's going downhill or decreasing. And then because it's x to the 5th, it's just going to look a little sharper than our normal cubic function. And it's just a sketch, so it doesn't have to be perfect. Okay, next up, negative 5x cubed. This transformation has an a value, so it is reflected down, but it's also a vertical stretch. So it's not moving to the right or left. Keep the starting point at the origin. But instead of going like this and having it be a decreasing function, we have to do the reflect and the stretch. So this point right here is going to reflect across, and it's going to stretch. So it's going to be 5 units away from the y-axis. So that point now becomes, instead of positive 1, it's negative 5. And this negative 1 becomes positive 5. So take this one away. Now we can see this is super stretched. It's almost going to look, the way I'm going to draw it, which is not perfect, it's going to kind of look like a line, but it is cubic. It's just that vertical stretch really stretches it out and makes it hard to see the turns. Okay, and the last one here we're going to look at is degree 4. So that's going to be opening up or down. In this case, because of that negative sign, it's going to open down. And let's make sure we get our transformations. Left 2 and up 4. So left 2 and up 4. And this is kind of going to look like a parabola that opens down. So over 1, down 1. But the rest of the points we're not going to mess with. We're just going to kind of sketch it out and make this look a little bit more squared off because it's a power of 4 instead of a power of 2. Okay, so what we're going to talk about is end behavior and the leading coefficient test. So the end behavior of a polynomial is kind of what's happening at the far left and the far right. When you get to calculus, it's going to be written like this. As x approaches infinity, f of x approaches, and then you'll say whatever value it approaches. We would also want to know, that would be what's happening at the right side of the graph as we get towards positive infinity. To say what's happening on the left, we say as x approaches negative infinity, what's happening to the y's? What is f of x approaching? So this sort of thing helps us understand a little bit about how our graphs are going to look generally. So what I want you to do right now is go ahead, go to Desmos, and you're going to type in these functions, and you're going to describe the end behavior. So I'll start you off with the first one. If we look at x cubed minus 2x squared minus x plus 1, we're going to look and see, okay, that degree is 3, which is odd. The leading coefficient is 1, and that's a positive number. And then you're going to look at the end behavior of the graph and kind of see what is it doing with its shape. And you'll notice it's going to have this kind of shape. We would say that end behavior is down, up. So we're just kind of representing those arrows at the right and the left. So pause here and go ahead and fill out the table. Okay, so hopefully you filled out that table now with the different degrees and the sign for the leading coefficient and then the end behavior arrow. So go ahead and check your work. And then let's kind of summarize what is going on here. So if we want to determine the end behavior, like what's happening at the right and left of the graph, using the degree and the leading coefficient, hopefully you noticed the pattern that when we had an even degree, the arrows went the same way. Right? Either up, up, or down, down. And when the leading coefficient was positive, it was up, up. When it was negative, it was down, down. When we had an odd degree, the arrows went opposite ways. And then when the leading coefficient was positive, it started low and ended high. Basically, it was increasing. If it was a negative leading coefficient, it started high and ended low. All right, so keep that handy to make sure you understand and you can quickly identify whether something's even or odd. We're going to wrap up with this little practice here. So I want you to go ahead and try these on your own. Describe the end behavior, so just up, up, down, 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 up, down, just do the arrows. And then for 7, 8, and 9, see if you can find the zeros by factoring. And then check back in here in a minute and I'll have the answers posted. Okay, so check your work here on the end behavior. On 7 we had an odd degree and a negative coefficient, so high, low. On number 8 we had an even degree and a negative coefficient, so down, down. And on number 9 we had an odd degree and a positive coefficient, so down, up. And then the same process for 10, 11, and 12. All right, the last thing we're going to do is have you find the zeros for 7, 8, and 9 by factoring. So that's my hint to you, factoring. And if you notice, all of these terms have x's, so you're going to take out a GCF. Pause here, give it a try, and then I'm going to post the work and answers. Okay, so check in on your factoring. These problems all have some unique things that I want to pay attention to. So all of them had a GCF to take out. And once you took that out, you were left with a difference of squares. For example, in number 7, x squared minus 4. Those always factor the same way. X minus 2x plus 2. There's sort of a formula to that. If you look in number 8, it was the same thing. X squared minus 1 factored as x minus 1 and plus 1. And even on the last one on number 9, x to the 4th minus 1, that's also a difference of squares. So you can factor those. If you have any questions on these solutions, the ones that were right here, talk to me about those next class. Have these ready because we are going to continue with our polynomial function lesson when I see you next week.